Hello everyone, welcome to this video. This video is going to be the single video you need to understand the basic of classic transformer architecture that later changed the world with AI technology. In this video, I'm going to break down the architecture into several key components and go through each component one by one. Let's dive into it.
I want to start with something seems unrelated. So how to smooth a noisy time series. So first graph, X. It's a noisy time series data. There's x0 to x55 numbers, and they form a vector X. Now we have a reweighing function. We call it W3 or X3. So it's a normal distribution-like function. What it does is it will filter data that's like far away of x3 and amplifies the data that's close. So if we multiply the filter reweighing function with the time series data x, like x0 multiply w03, x1 to w01, and we add all the values together, we're going to get a new value y3. So here is the mathematical formula. y3 equals to w3 dot product x. Similarly, y4 equals to w4 dot product x. w3 is a vector, x is a vector, so y3 is a number. Similarly, y4 is a number. And then with all the y0 to y5, it forms a new vector y. And this vector is supposed to be better than x. The advantage is vector y now have like other points context compared with x. So it's less noisy. So you can say y3 paid attention to other points. Similarly, from y0 to y5, they all paid attention to other points. I want to also say it's not necessarily like smoothing this function. It really depends on how you design the reweighing function, right? If your reweighing function is just flat, then your output y is going to be flat. If your reweighing function is just extremely pointy, say only w3 have value and all the others all 0, then it basically does nothing. Your y will just look like identical with x. So it really depends on how you design your reweighing function. Okay, the important thing is you understand with some reweighing function, now you have a new vector from x, and this new vector y have the advantage of it has context. Okay, let's move to the next one. Before I talk more about transformer and natural language, I want to talk a little about word embedding. Word embedding is the representation of word, which is the smallest representation in the natural language. So the definition is a word embedding is the representation of word. The embedding is used in text analysis. Typically, the representation is a real valued vector that encodes the meaning of the word in such a way that the words that are closer in vector space are expected to be similar in meaning. That's a very long sentence, right? I want to show some example here. Let's simplify this word embedding. Let's say in the vector, there's 5 values and each of them is 0 or 1. In reality, it usually is a score. But let's say it's 0 and 1. It's a vector, and first one is human, second is female, third one is male, and then it's bark or not, and then it's talk or not. Then for the word father representation, the word embedding is 1, 0, 1, 0, 1, right? It's human, it's not female, it's male, that doesn't bark, talks. The representation of stud is 0, 0, 1, 1, 0. It's not human, not female, it's male. It barks, it doesn't talk. So this is a pretty simple example of word embedding. So why is it useful? There are two big advantages, I would say. First one is the distance between vectors indicates the similarity between words. So you can actually take a look at these examples. From king to queen, the vector is very similar to from man and woman, right? It captures real relationship in the real world. Similarly to walking and walked, swimming to swam, and then like country capital relationship. The distance between the the word embedding is a vector and it indicates some kind of relationship. The next one is words with similar meanings are represented by similar vectors. What it does is, in the end, it aggregates similar entities in very close clusters. This is a 2D representation, but in reality it's very high dimensional. But it's just for you to see, like train, bus, car is clustered similarly. College, school, work, it's one cluster, and on and with similar meaning words are represented by similar vectors. So now we know about word embeddings. So let's talk about the tension for it, like natural language. So here's a sentence. Date is my favorite fruit. Date is a word that we use very commonly, right? And I would say 90% of the time it refers to the time instead of a like edible fruit. But like, how do we human knows date means fruit in this, something to eat in this case? It's like human, we read the sentence and we see, okay, there's a fruit and this fruit is referring to this date. So that's why date in this sentence is something to eat rather than the time. So similarly, when you try to tell the AI system like this has some other meaning, you can use a tension like mechanism, right? So imagine like natural language needs the similar mechanism, like each word or token or data point needs context of others in the same sentence or paragraph. So for example, date in this sentence means an edible fruit instead of time, with the context provided by this fruit. However, this context is different from the previous context, right? The previous example, when we say context, it's basically similar, like proximity, our like filtering function. But we can't use proximity like we did before. We need a more sophisticated reweighing method, and it needs to have semantic meaning. So let's move on to the next one. So let's say here is a black box of reweigh and linear reprocess. We first partition date is my favorite fruit to like different word embeddings. So we can do mathematical process to this natural language. V1 is the word embedding of date, V2 is the word embedding of is, etc. And then we input this word embedding to this big box, supposed to be the attention mechanism. And then the output is going to be y1, y2, y3, y4, y5. And what we want is y1 is a better representation than v1 because it has more context of other words. So this y representation should have more context than v. What we do is usually like this. v1 is a vector. So dot product v1, it's a number. So it's a real value w11 with star. Similarly with all the w12, 13, 14, 15 star. And then we normalize it. So they add up to the value 1. This is the weight that we need. And then we use this weight to reweigh v1. w11 dot product, not dot product. This is a real value. This is a vector. So w11 multiply v1, and then same with v5. And we have a new vector. This is like a linear reweigh y1. So reweigh all vector towards v1, so it has a context of other words embedding. We do similar process for all the other vectors, y2, y3, y4, y5. And we have the new representation of date is my favorite fruit. And now the y vector have context. And this is the basic for attention mechanism in natural language. Before transformer, the most popular model for natural language is LSTM. So I want to spend some time to talk about it. LSTM is a recurrent neural network. A traditional RNN has a single hidden state that is passed through time, and that can make it difficult for the network to learn like long-term dependencies. LSTM model solved this problem by introducing a memory cell. This is a container that can hold information for an extended period. So it makes LSTM like capable of learning long-term dependency in sequential data. It works great at that time for language translation, speech recognition, and time series forecasting. So on the right, there is the LSTM cell. However, there's a problem with it. So LSTMs are slow and less efficient than transformer due to their sequential nature. Which means the training phase, we need to pass the sequential data one at a time. On the right hand side, there's the transformer architecture. You can see it is very different from the previous LSTM. Transformers can capture global dependencies more effectively in long sequence compared to LSTM and others like GRUs. As a result, a transformer is better at parallelizing compute. The intuition is, for example, in episode 1, when we have a sentence, we don't have to pass in one word at a time. We actually pass everything as the input embedding at once. It makes the calculation a lot more effective, and if we can parallelize the computation, it scales up a lot better than LSTM. Of course, there are like other stuff that makes transformer works, and position encoding is one of them. As you can see on the right hand side, input and then input embedding, and then the next step is we need to add like positional encoding. What is position encoding then? So as we discussed before, self-attention mechanism captures dependency and context. So in short, date normally refers to time, but when we know there in the sentence there's another word fruit, it captures the context from fruit. In this case, date most likely refer to the edible fruit instead of the time. However, in language, order matters. This is the most classical example that you're going to see everywhere. Here's why order matters. So even though she did not win the award, she was satisfied. That is one sentence. The other almost identical sentences, even though she did win the award, she was not satisfied. They have the same character, same word, but the order is different and the meaning is completely different. Other than the context, the previous mechanism that captures context, obviously we need a way to know the position. And previously we know the relative position based on the index of the word embedding, but that's not enough. We need something similar to a embedding. So that is the position encoding here. A naive way is we need another embedding for position. The most naive approach is we just put the position of the word as the embedding, right? For example, first word, E0 stands for the word embedding for the first word. P0 stands for the position encoding for the first word. And because it's the first word, the index is 0, so P0 will be all 0. Similarly, P1 will be all ones, and Pn will be all n's. Like, will this work? This is not working, since like large n's will skew all the embeddings. Like you can imagine if the sentence is like 100 word long, En plus Pn, that is the new input for the nth position. The embedding will be a lot larger than E0 plus P0, so the result will all be skewed. So we need to bound min and max value, and we still want it to be able to differentiate like the position info, like whether it's the real position or the encoded position. So let's try something else. We include normalization in it. We normalize it by the first P0 is all 0, P1 is like 1 over n. That means for Pn it's 1, right? In this case, all the values is between 0 and 1. So this won't work perfectly either. And there are some caveats, like encoding for the same word combination will have different encodings. The sentence length is different. Here's an example. There is two sentences. I am a dad, which is 4 characters long, 4 word long, and there is I am Martin, that is 3 words long. And in these two sentences, the sub-sentence I am, those position encoding will be different. And we don't want that. We want it to be ideally to be the same. So we need another property, which is the encoding ideally it's not dependent on the length of the sentence. So what's the actual solution here? The proposed solution is actually very smart. So as you can see, this is the two formula of the position encoding. POS is the position of the word, And it's so for first word is P0, for second is P1, this is typo, and then P2, P4, P2, P3. So D is the dimension of the embedding for the words. In this case, our word embedding have 5 dimensions. 2i, it means the even indices of position encoding, like within those D dimensions. So 0, 2, 4. 2i plus 1 is the odd indices. And you can, for the even values, you just use the first sine formula. For odd position, you use the second one, cosine value. Just to clarify, all the values I put here is fake. Just put random numbers. So now we combine the semantic embedding, which is E0, E1, E2, E3, and the position encoding, which is the P0, P1, P2, P3. We combine those and we have a positionally aware semantic embeddings, which is what we want. So now we have the perfect input for the transformer model. So then we are ready to dive deeper into what actually happens in the transformer model and how attention mechanism is actually using these semantic, positionally aware semantic embeddings. This is the intuition. This graph on the right-hand side, it's for even indices. 2i equals to 0, 2i equals to 2, 2i equals to 4. They have similar sign graph, but they have different frequencies, right? And they have those properties that we want. They have bound min and max values, 1 and -1, and they're able to differentiate encoded position info. Like for example, even let's say for I equals to 2i equals to 0, there's like 2 points, 2 word position, they have the same value for I equals to 0. If you take a look and see like for I equal 2i equals to 2 and 2i equals to 4, the value is going to be different. So in this way, the encoded position, the position encoding is actually different, even if let's say for I equals to 0, they're the same, they have the same value. For the other 2 i's, they're going to have different values. This algorithm is able to differentiate encoded position. And we know they're not dependent on the length of the sentence. So for I am Martin and I am a dad, the I am like common prefix will have the same encoded position encoding. So let's do a quick recap. So on the first episode, I went through the simplified attention mechanism using some examples. I started with smoothing a time series with using a normal distribution-like filter. And then I moved the example from time series to natural language. So I want each word in the sentence to get some context of other words, just like what we did in the time series. I use the example of date is my favorite fruit. V vector is the word embedding, and when after we go through the attention mechanism, we get a Y vectors. And Y has more context taken into consideration compared with V, including the position encoding that we went through on the second episode. So this is achieved by attention mechanism. And here is the attention mechanisms formula that's in the original paper. So now let's dive deeper into what actually happened to this formula. So this is still the recap. When we transform V to Y, we go through the dot product to get some weight, and then we normalize it so they sum up to 1, and then we apply the weight and reweigh V vector so we get Y1. And we did similar stuff for Y2 and Y through Y5. So let's modularize this a little bit so it's clearer. So this is a modularized view of the previous mathematical calculation. And this time I'm going to use a shorter example, which is I am Martin. So these 3 words, each of them has a word embedding V1, V2, and V3. And let's assume a word embedding is 1 over 4s in dimension. Let's say in this case, we want to get the third word, which is Martin's context on all the whole sentence. In this case, V3 is right here. In this case, I want to use database analogy, which is queries, keys, and values. In this case, I want the context, I want an attention representation of the third word, V3. So V3 is the query here. And in order to get what I want for V3, I need to go through a bunch of key value search as in database analogy. So if the key is v1, then the value is v1. Here is the second key and then the second value. I understand this might not mean a lot, but this is just to help you to understand why we are calling these query keys and values. It might not make total sense at all. Let's say v3 is the query here. What we're gonna do, as in previous math calculation, we first have to go through the dot product. v1, v3 will get r1, v2, v3 will get r2, v3 will get r3, and those are three real value, which is like three numbers. And then we normalize those three numbers so the sum equals to 1, and this is the weight. And then we apply the weight and reweigh the whole v vector and get the y3 here. And we can also go through similar operation to get y1 and y2. This is the contextualized attention representation of I and n. So this is the modularized view of previous calculation. So let's add more to it right now. So as you can see right now, there's no weight at all. And if you have work in machine learning, whether it's classical or deep learning, you know, everything is about learning the correct weights. So let's add some weight to it. Now we have three weight matrix, mk, mv, and mq. Each one for a query, one for key, and one for value. The weights should be able to generalize the learning capability. Just for simplification purpose, let's say the dimension is 4/4. So in this case, when we multiply the original vector, it won't change the dimensions. 1/4 multiplied by 4/4, it's still 1/4. So this is just simplification. In reality, when we go through this is a linear matrix multiplication, right? So in actual productionization, this is called linear layer. When we go through linear layer, whether here or later after concatenation, I'm gonna go through it in later episodes. The dimension usually will change, either increasing or decreasing. But just for simplification purpose, let's say right now it's 4/4, so the dimension won't change. This won't change this graph too much, just will make the small v to big V. And then now we have weights, so now we can generalize the learning capability, so the weight will contain more information. So let's simplify this view a little bit more. And now we can have this graph. The word embedding go through three linear layer, which is the matrix multiplication with MV, MQ, and MV. So we get keys, queries, values, and then for keys and queries, we do a matrix multiplication. And then we go through a normalization. In the last slide, for simplification, we just normalize it to sum to 1. But in reality, we should do softmax, we should do scale, we should also mask if you're going through inference. And then after we get the attention scores, we do a matrix multiplication with the values matrix. And then we get a y vector here. As you can see, this is basically attention formula. QKT is this part, and the softmax and the scale is this part. And then you do another multiplication with V. This is a more detailed view of the whole attention block in the transformer paper. And as you can see, there are multiple attention blocks. And don't worry, I'm gonna go through all of them one by one in later episodes. Take a look into the attention block details. You can see there's linear layers for VKQ as we discussed, and then they all go through a dot product attention, which is the matrix multiplication, and then scale, and then mask for inference. In our case, we still haven't discussed this yet. And then go through softmax, and then matrix multiplication with V again. Afterwards, we're going to go through concatenation because it's multi-head, and we're going to go through linear layer to drop the dimension again. So now we have went through the mathematical details of how we get the attention with K, Q, and V. There are left several questions. So first one is, why do we scale? Why are we scaling over this number here? The answer is the key query vector could be very large. So when we do dot product, it could be disproportionately large. And for that large number, when we do actual training, this can lead to vanishing gradients or exploding gradients that will the training, so it's learning too fast or too slow. So if you want to learn more about these two concepts, you can Google it on your own. Next one is why use this number to be specific as the scaling factor. So mean 0, variance 1, this is a typo, is standard normal distribution. And if we assume Q, K are decay dimensional vectors whose components are independent random variables that follow the standard normal distribution, their dot products will have a mean of 0 and variance of dk. We want the distribution to be standard, so the variance should be equal to 1. So in this case, the values won't be too scattered. In order to get this variance, so we want to divide by this specific scaling factor. So this is the math reasoning behind it. The last one is why do we want to do softmax? This is pretty standard actually. After the mathematical calculation, we get a bunch of attention scores. We use softmax to transform the attention scores to a probability distribution that sums up to 1, which is very convenient for us. We talk about the attention mechanism, and we know it can capture context and relationship between tokens. However, natural language is a very complex problem and usually have multiple aspects of context and relationship. For example, in this sentence, date is my favorite fruit. We know date is a fruit, and we know date is my favorite fruit, and we know the concept of favorites applies to a date. And there are a lot more actually. For example, we know this language, this sentence probably has a neutral mood or even like a neutral to positive mood because we're talking about our favorite stuff. So there are a lot of complex and multiple layers of context and relationship in just one simple sentence. Are we only going to use one type of attention to capture it? The answer is no. We usually use different set of parameters to capture different type of context and relationship. And sometimes we don't even know what is the type of relationship. We just use a different set of parameters. This is a example for natural language. Next, I'm gonna also show an example for computer vision. Transformer is a very powerful tool. Don't get me wrong, it's not only useful for natural language, we also use it for computer vision. This is one example of different attention mechanisms intuition. We have an image with a full background, and there's 3 filters. There's 3 attention mechanisms. First one, attention filter 1, just figure out who's the person. This is Hua Mulan. And then the second attention focus on figuring out what is the sky. And the third one focus on figuring out what is the mountains. So this is another example, intuition of attention mechanism and why we need multiple different types of them. This was the previous attention block that I went through. So we already know with the input word embedding plus position embedding, we go through linear layers. And then for key and queries, after we go through linear layers, we go through matrix multiplication, and then we go through softmax, scale, ignore mask. I'm going to talk about it in the next section. And then we also do another matrix multiplication with values and get the attention scores. So the question is, how do we introduce the multi-headness of attention to this problem? So this is multi-head attention block. We basically have the same input. The input dimension doesn't change. But when it goes through the different blocks, now we go through multiple head. Let's say for the first one, we call it head 1, and for the last one, we call it head H. So H is the number of heads we are going to go through, and each of them focus on capturing one specific relationship. It still go through the linear layers and still keys, queries, values, still go through the matrix multiplication, still go through normalization and matrix multiplication with values. But now, since there are H heads, now we have H y vectors, right? And each y vector is with the same dimension of v. But then we also said before, we want the output dimension to be the same as the input dimension. So we can like layer hundreds of attention block. But this way, the output dimension is h times of input. So how do we solve this? We solve it by first concatenate all of the result. So we append one after one. And we get a n multiplied by h dimensions of y vectors. And then we go through the linear layer again, and this time the linear layer's focus is just to remap the dimension back to n, and we get another y to yn. This is a typo actually. This y1 is actually different from the y1 here. So it's a different vectors. The dimension is the same with v, but it's from multi-head. So how do we achieve this? Right? How can we use linear layer to drop the dimension from n multiplied by h to n? Before I show that, I just want to say previously we went through the scaled dot product attention. We went through the linear layer here. This time we were focusing on the concat and linear layer here. So the way linear layer works is like this. So linear layer, I've heard like all other names people call it. I've heard dense layers, I've heard fully connected layer. So they're all pointing to the same like concept. Let's say y is the input and v is the output of the layers. Then we actually have all of them fully connected. This is just a view of it. In between there could be like multiple layers of fully connected layer. And in this way, we are able to map the input to output, and we can also change the input dimension to the output dimension that we want. In this case, the example is we change a 5x1 dimension to 3x1 dimension. So this is how linear or dense or fully connected layer drop the concatenated dimensions back to the original dimension that we want. On the right hand side, there's the transformer encoder decoder architecture. And one important thing to know is the training and inference phase is actually a little different. Transformer behaves differently, at least this encoder decoder architecture behaves differently. The main difference occurs in the decoder, which is the right hand side part. During training, we know the entire output sentence and we can pass it to the decoder all at once. For example, if we're trying to do a translation service from 我是马丁 to I am Martin, we can pass 我是马丁 into inputs, and we can pass I am Martin to outputs, and we can pass a bunch of training translations to this input and outputs during training phase. However, during inference, the decoder must generate one word at a time in an auto-regressive manner. Then the decoder uses like previously predicted words to help to predict the next word. That means you have to output one word at a time. This is just the nature of the application you are going to use. A bunch of time, decoder is just doing translation or text generation. What's already generated, it's already out there. You're not going to change it. How to achieve that is by mask attention. So this is the mask attention module. It will make sure each token in a sequence only attends to previous tokens and itself, not future tokens, which means the tokens generated, the word generated, it all depends on itself and its previous token. It's not going to depend on anything in the future. This is an example. Obviously, this is an oversimplified version. In the token embedding stuff, there is start of sentence token, and when it ends, there's end of sentence token. But this is like a simplified version. Let's say we want to translate I am Martin to Chinese, and the encoder input is going to be I am Martin. And we do the position encoding, and then we do the multi-head attention, at and norm, feed forward, another at and norm, which I'm going to cover in the later episodes. The encoder part is pretty straightforward that we have covered in previous episodes. So the decoder, as I mentioned, it's not going to put the whole output sequence because this is not training data. We're trying to translate an unknown sequence, which is an I am Martin. So the first decoder input, it's a start of sentence token, and then an output that go through all the decoder, and an output will be the first translation, 我, which is Chinese stands for I. And then we've used this token to pass to the output, to pass it to the decoder again, and then we get the next generated Chinese character, which is 是, that is the Chinese for am. Similarly, we pass in the combined 我是 to the decoder input, and then we get the next two generated token, which is 马丁, Chinese stands for Martin. So this is oversimplified version of how decoder works in the inference phase. We can get into a little detail into the mathematics, and then you're gonna know the one very important concept, that is the KV cache. So during inference autoregression, at each generation step, we are recalculating the same previous token attention. So this is assuming we don't have any cache. We are not storing anything in memory. This mathematic step, hopefully you are familiar with it. I have gone through it in our previous episodes. Let's say the first token comes, and then we go through the QKTB. I ignore the scale, the softmax, just to leave out the QKTMB for simplicity. QKT is the matrix multiplication, and then another matrix multiplication, and then you get the output. So as you can see, the size of the calculation is 1 multiplied by embedding size. Sorry, this is a typo. Embedding size. Q1 is the embedding, so this size of Q is 1 by embedding size. Same with embedding size over 1, and then this is 1 embedding size, and then you get 1 by 1, and 1 by embedding size, and then the output is 1 by embedding. And then when the second token comes, because you're not storing anything, right? You have to pass, as I said, you have to pass the whole sequence into the decoder. So you pass Q1, Q2, and then in order to get the whole attention matrix, you need to do K1, K2, and then Y1, Y2. And then when it passed the mask attention module, instead of showing all the 4 attention scores, it used a mask to basically mask out all the future tokens. For example, in this case, this one is Q1, K2. So the first token, K2, is something in the future, right? So you're not going to have access to it. So that is masked. And then that will guarantee the O1 is only generated by token 1 or previous. It's going to guarantee O2 is generated by token 2 or previous tokens. And then the third query token comes, and then you have to pass in the whole sequence, do this, and then do the mask. Similarly, you're going to mask out all the previous tokens, which is basically the upper right part of the matrix. And then you get the 3 outputs. So as you can see, as the time goes, the size of the calculation is growing exponentially, right? Let's say time is, the first one is t equals to 1, and then t equals to 2, and t equals to 3. So obviously the dimension of this matrix is t squared, right? So it's quadratic. Now let's go with inference with KV cache. So as you can imagine, KV cache is just trying to cache the key and value embedding. Q1 is the same. When Q2 comes, all you need is actually this QKT. In order to get O2, you actually just need this calculation. And this calculation, you only need K1 and V1. So if we already cache it, let's say green means cache it, you can only focus on Q2 itself. You don't have to focus on whatever Q1 says. So you store K1 and V1 into memory, and then you are able to get this QKT, which is 1 by 2, and then you multiply by V vector, and then you get the next output. Similarly with Q3, when a new Q token comes, since you are already storing previous Ks and 1s, you can get the QKT to calculate O3 directly. And the matrix multiplication, the complexity, like intuitively, right now no longer quadratic, right? It's linear to t. Let's say t equals to 1, t equals to 2, and t equals to 3. So it drops the complexity of matrix calculation a lot, which is what matters in machine learning, right? It's flops, a floating point operation per second. So this is the KV cache trade-off. What is good, The plus is number of flops floating point operation per second drops. It drops from OT squared to OT. T is the length of the sequence, I would say. The downside is we need extra memory, right? You need to store K and V embeddings. So the memory amount we needed is the size of 2 multiplied by number of tokens, multiplied by number of layers, and then multiply number of KV heads, and then multiply KV dimensions. The 2 as in you have to score both key and value. The number of tokens should be easy to understand. KV head we went through a previous episode. KV dimension, similarly we went through a previous episode. The number of layers here, this is something people usually ignore. The neural network I show here, it's all simplified version. It usually have hidden layers. So for each attention module and feed-forward module, all of them are multi-layers. So you have to go through a bunch of hidden layers. You have to consider also the number of layers to store all the K and Vs. And then that's the KV cache eligibility. So when can you use KV cache? I kind of already gone through it when I introduced KV cache. Right? You need to have causal relationships. So new tokens attention calculation only depend on itself and previous tokens. So if it's depend on future token, then you can't use KV cache. For example, there are BERT, the famous, at least it used to be famous, encoder transformer architecture. If you use BERT to do natural language processing, you're going to see the output changes when it processes the token. That is because it's not a generative AI. The generated token is not fixed, so it kind of changes the output when it process the whole input. So in that case, we cannot use KV cache anymore. Most of the generative AI models right now, for example, GPTs, DeepSeek is also a generative. There's decoder-only architecture. It also have KV cache component. It's slightly different, but it still have the same mechanism, which I'm gonna go through in another series. First of all, let's start with the different attentions in the classic transformer encoder-decoder architecture. As I covered before, in the encoder there is a self-attention module, and in the decoder there's a mask multi-head attention, there's another cross-attention multi-head attention. Yes, I think I've already said at least 10 attentions, so hopefully this is not confusing. I'm gonna go through each of them one by one in the later slides. First of all, I want to build an intuition on attention mechanism. So this graph I use a lot in my previous slides. So this is a modularized view of what attention module is doing within. Basically, it's a matrix multiplication, like a dot product for keys and queries after the linear transformation. And then it's going to go through a normalization, which is basically softmax and scale. For mask, there is a mask. Basically, it's softmax plus scale. And then we do another matrix multiplication with values after its linear transformation, and then we get the output. So the intuition is matrix multiplication number 1 is the dot product cosine similarity between key and query. And the normalization is the softmax to map similarities through a probability space. And then scale is to prevent gradient diminishing or explosion. And the second matrix multiplication is applying the similarity distribution to reweigh value. So you can think about, first one is cosine similarity dot product. Second one is a bunch of normalization to map it to probability space. And then second matrix multiplication is apply that probability and reweigh the values. So that is the intuition of attention. Let's start with the first, basic attention. Let me remind you that transformer is based on the concept of self-attention. Before self-attention, there's actually attention. So attention is a very long-lived concept already. And in this case, let's say we have 2 sentences. First one is, I have a white cat. That is say a query. And then there's a second sentence is, I love little animals. And we want to know what's the similarity scores, what's the attention scores between these two queries, we can calculate it based on their word embeddings and dot products. And we're going to get this matrix. So this is the basic attention. It's trying to get similarity or attention scores between these two queries using dot product cosine similarity. And then we have self-attention. What's the difference between basic attention and self-attention then? Query equals to key, right? That's why it's called self-attention. And then we have the cross-attention in the decoder. The cross-attention layer is trying to get the similarity scores between the input and between the output. So the keys and value is going to come from encoder. Let's say the input is I am Martin. It's trying to do a translation from I am Martin to Mandarin. So the encoder inputs I am Martin, and then after a linear layer, it gets the keys and values matrix. And then the decoder, let's say it already translated I am to 我是. And we're gonna use the decoder input and do linear transformation to get the query matrix. And then we do the same dot product similarity score to see the similarity between output sequence and input sequence. And then after normalization, we get the matrix, and reweigh, we get the next translation, which is Ma, M-A-R in Martin. Cross-attention is to establish relationship between input sequence and generated output. So the attention cosine similarity happens between decoder query, encoder key, and the similarity will apply weight to value, which is the encoder value. We want the attention score between encoder and decoder. This is the example. Encoder is I am Martin, decoder is 我是, which is basically the translation of I am. Okay, so the next concept is mask attention. Causal mask is applied to attention mechanism to ensure a model predicts each token in a sequence solely based on the previous tokens, not on any future tokens. So what it means is for generative models, let's say GPTs, DeepSeek, those are all generative models. So the token generated only depend on previous token, not future tokens, which means in the similarity in the attention matrix, we need a mask out future keys and values. In this case, if the query is from the first token, we don't need anything from second and third. And for the second query, we don't need anything from the third. And for the third query, we can have everything. So basically, we apply a mask. This actually enables KV cache to speed up transformer. So we can actually cache keys and values to speed up transformer at the cost of memory. So the pros and cons, you can refer to my previous KV cache episode. So then now we use KV cache and mask attention to optimize transformers performance. Then we hit another bottleneck. KV cache memory size becomes the bottleneck, especially when the sequence is longer and longer, because the memory is linear with the sequence, even with KV cache and mask attention. Engineers and scientists will think about different ways to address the bottleneck. So then people start thinking about, can we reduce the KV cache and not hurt the quality? There's the group query attention and multi-query attention. Let's start with the multi-query attention, which is a bit of extreme. It shares a single key and single value head across all query heads, which can significantly reduce memory usage, but also impacting the accuracy of attention. So as you can see, this is the classic multi-head attention. The keys and values will be cached in memory. So in multi-query attention, we're going to reduce those to one key and one value. Obviously, it's dropping the memory size, but it will also impact quality. Group query attention is somewhere in between the classic and the multi-query attention. So it's an interpolating method between MHA and MQA, where a single pair of key and value heads will be shared only by a group of query heads, not all queries. So the quality impact is less, and it still saves tons of memory. You can merge 2 to 1 or 3 to 1, or based off some similarity scores to merge different queries. So a lot of method can be used. If you want to know the details, you can actually refer to my DeepSeek technical report. It contains a bunch of information about GQA and MQA. So now this is the last concrete example I have. which is the MLA. Basically, this is one of the reasons why DeepSeek can achieve great quality with very cheap cost. So they use what they call MLA attention mechanism that projects the keys and values into a lower dimension space. And they use some really smart way, like doing customized operation with rope and then concatenate compressed keys with non-compressed keys to get the actual attention. So they use some very innovative mechanism to speed up the classic attention mechanism. So this is a very heavily customized attention mechanism, and it's just one example of it. There are a lot of variances of the classic attention mechanism, and each of them did different customizations to solve different performance problems or quality problems. So don't be surprised if you're going to see more and more variances of transformer. Just keep in mind of the original concept of it. Matrix multiplication, you get the cosine similarity scores for dot product, and then use normalization to normalize it so we can use it for later, and then you apply the similarity distribution to reweight the value. This is the basic intuition of attention.
So first of all, why name it feed-forward? So this concept is actually comparing to another concept, which is recurrent network. Before transformer, recurrent network is mainly used in machine translation, text recognition, etc. And there's a reason for that. So because recurrent neural network can process information in loops, so this allows information from previous steps from the past to be fed back into the network. So this is great for sequential data because it holds some memory. So text recognition, machine translation, this model works perfectly. And you must have heard of LSTM, it's a variant of this RNN. So in the contrast, we have feed-forward neural network. So in this case, the information flows in one single direction with no circle. So this is good for tasks that doesn't require memory of past data, say image recognition. Of course, this is before transformer. As we have gone through already, transformer is pretty creative in doing self-attention and then position embedding to make sure we can have the whole context, but still do it in parallel instead of going through sequential. So this is the feed-forward architecture. It's the most simple deep neural network you're gonna see. So it has input layer, it has output layer, and it has one or multiple hidden layers. So the first layer is input, the last layer is output, and everything in between is hidden layers. Let's take a look at feed-forward network inside transformer. So inside transformer, you can see there's two blue blocks, that is feed-forward, and it all followed by a add and norm. Today we're also going to talk briefly about add and norm. First of all, let's take a look at the basics. The formula of feed-forward network is this. So as you can see, there's a max 0, x w1 plus b1, and then w2 plus b2. So this is basically two linear transformation. The first one is x w1 plus b1. The next one is w2, this whole blocks plus b2. So there are two linear transformation with a ReLU activation function in between. So what is a ReLU activation function? So it is a nonlinear activation function used in neural network. ReLU x equals to max 0 and x. So the larger value between 0 and x. So this is the ReLU part. And it's happening in between the two linear transformations. So the intuition between these formula is, within this formula is, again, thanks Gemini, you made this part really easy. So the first one is nonlinearity. The first fully connected layer projects the input to a higher dimension space. So this allows the network to learn more complex relationship. And then it goes through the activation function. So this is the part where it applies the nonlinear complex relationships. And then we go through the dimensionality reduction. It happens in the second fully connected layer. So it projects the data back to its original dimensionality, ensure compatibility with the next layer. So after these two, it actually learns a lot more, not only because of we expand the dimension in the first connected layer. More importantly, ReLU actually makes sure it learns nonlinear relationship. Remember, in our attention block, everything is linear. So this is the place we learn nonlinear relationships. And then it also have the advantage of parallel processing. So since each position in a sequence is processed separately through the FFN, the computation can actually be parallelized efficiently. So this is not in the graph, but it's a pretty standard exercise that is applying dropout. Dropout is a regularization technique used to prevent overfitting, which is very common in machine learning by randomly dropping out, that is, set the neurons to zeros, a certain percentage of neurons during training. So this forced the network to learn more robust features and not rely too heavily on any single neuron. So this will also improve the ability to generalize to new data. So the advantage is basically covered in the summarization, in the summary. So it reduced overfitting. It reduced overfitting by preventing neurons from co-adapting too much. And then it also improved generalization. It forced the network to learn features that are not dependent on any specific neurons. After it go through this, we usually have dropout. And then there comes the add and norm. So this is not in the blue block, but this follows the blue block. Add and norm means the first one is add. It means residual connection. This is also a common practice in deep learning. So before I talk about this, you can take a look at the graph on the right-hand side. X is, let's say, some input, and some of it is going to go through the deep neural network, including ReLU, and then it's going to get the fx, which is the gradients. And then instead of passing the gradients directly through the next layer, it also adds its own function. It also adds its own, like, identity function is just a fancy way of saying itself. So this actually helps a lot in mitigating the vanishing gradients problem. The goal is to, as I said, mitigate the vanishing gradient problem for deep neural networks. So this happens originally from ResNet, and now it's used more in deep neural networks, say transformer. So this enables the deeper architecture by, of course, resolving the vanishing gradient problem, which is more serious as layers increase. So how it does is it allows gradient to bypass immediate layers, and adding identity function with the reweighted values. So this is the feed forward, this is the add and norm, and as you can see, the identity function goes directly through add and norm, and also some of it go through the feed forward, and then we add in this place. So we have went through the add part, and then let's talk about the norm. So the norm, usually in transformer or sequential like LLMs, it refers to layer normalization. So layer normalization is a technique that helps stabilize and accelerate training by normalizing the inputs to each layer. So it ensures the model processes information consistently regardless of the input scale or distribution. I know it doesn't mean a lot, but we can use next episode to talk about layer normalization. And I want to also compare with other normalization. So what is normalization? From Wikipedia, normalization means adjusting values measured on different scales to a common scale. If you Google normalization, most likely you're going to see two common ways of doing normalization. The first one is called min-max normalization, and the denominator is x minus minimum of x, the denominator is maximum of x minus minimum of x. So in this way, we can do a rescale for the value x. The next one is called z-score normalization. This one is doing not only rescale, but also recenter. With z-score normalization, it's gonna normalize your distribution to standard distribution. And it's done by minusing the mean and then divide by the standard deviation. If you have statistic background in your university, most likely they have gone through a similar concept. If you forget about this, just Google it and it should be relatively simple to pick up. So why normalization in deep learning? There are many benefits. It helps stabilize the training process by ensuring features are on a similar scale, preventing features with large values from dominating the learning process, which leads to faster convergence and improved model performance. So the first one is pretty obvious on faster convergence. By scaling features to a similar range, the gradient descent optimization algorithm can update weights more effectively, leading to a quicker training times. The second one is improved generalization. Normalization can help the model generalize better to unseen data by reducing the sensitivity to feature scales. The third one is stability in gradient calculations. So when features have vastly different scales, it can lead to very unstable gradients in backpropagation. Normalization can help mitigate this issue, whether it's vanishing or exploding gradients. The fourth one is pretty important. It reduced the internal covariate shift. So this is especially true for batch normalization. Normalizing activations within each layer helps to maintain a stable distribution throughout the network. This is very crucial for our deep architecture. I'm going to go through more details with example later. This is an example of how internal covariate shift can happen. Let's say your training data is training from actual cats and dogs, and obviously they follow some kind of distributions. And when you actually do testing, it turns out all the testing data is actually cartoons, which is a little bit, the distribution is different from your training data. And if you don't do any batch normalization, it's very likely it won't perform well on testing data because of the internal covariate shift. So this can confuse the model a lot. I take this example from this website. Where to apply normalization in deep learning? Usually you can normalize input data. For example, the data that you feed into neural network can be normalized before entering the network. This is basically pre-processing. The next place is activations. This is more relevant to our talk today. So we can also normalize the activations, which is outputs from the hidden layers neurons in the neural network. This is often done to stabilize and accelerate training, especially in deep networks. So first, let's go through batch normalization. For simplicity, I just pull out a layer with 4 neurons from a deep neural network. So it has 4 neurons representing 4 features, let's say x1, x2, x3, x4. And then this is a mini batch with 3 samples. And the sample value is just random. I just come up with random numbers. Batch normalization means we're going to do normalization and we're going to do calculation of mean and standard deviation for each row, like for each feature. So for x1, the mean is 5.3, standard deviation is 4.9. Similarly, for x2, this row, we get mean and standard deviation. And then for x3, we do another calculation. For x4, we do another round of calculation. So normalization happens across mini batch. It's independent for each feature. After we get the standard deviation and mean, for all features, we apply the following 2 activations and get a normalized value. The normalized value equals to the z-score normalization, which is the original value minus mean over standard deviation. After that, we apply an additional scaling and shifting parameter. So each node or neuron have learning parameter gamma and beta to represent the scaling and shifting. So the scaling is obviously this gamma and this beta is shifting. So these two values are learnable. So why is batch normalization not used for transformer? So batch normalization have its own limitations. So in batch normalization, the mean and standard deviation are calculated within the current mini batch. However, when the batch size is small, the sample mean and sample standard deviation are not representative enough of the actual distribution. And for a sequential model, we see smaller batch sizes because the sequence is very long. This usually happens to allow a model to update its parameter more frequently with smaller subsets of data. The transformer is very popular among the sequential model, right? So it usually have small batch sizes very often. So batch normalization doesn't work very well. And to be more specific, we usually do padding, which means adding zeros to make sure the data size is consistent, to make the input size equal during self-attention, which is not part of the original data and can mislead the model a lot. So this is an example. Let's say we have two input. The first one is hello, exclamation mark, and then my name is Martin. And in order for us to go through the self-attention matrix, because the dimension is fixed, we actually have to add two paddings for the first input. So padding will be all zeros. And when we do normalization using this, it's going to confuse the model a lot because we have to include this unnecessarily zero values. So what's the solution then? The solution is to do layer normalization. So layer normalization is very popular in sequential dataset. And again, I'm going to use an example of one easy 4-neuron input layer. And then again, it represents 4 features. And then the sample output within the mini batch is all random. This time when we do the mean and standard deviation calculation, it actually happens across features. It's independent of each sample. So we get the mean and standard deviation of all the features here, and then all the features on the second sample, and all the features of the third sample. So in this way, we actually don't have to do padding at all. For all the features, we apply the followings to activations and get a normalization value similar to batch normalization. And then again, we apply the scaling and shifting similar with the batch normalization. So this is layer normalization. Next, I want to talk a little about the RMS normalization, which is a relatively new normalization method, and it's catching up in popularity. So RMS norm normalizes the activations by dividing them by the root mean square of the activations for each layer. So unlike layer norm, RMS norm typically does not center the activations by subtracting the mean before normalization. It does include scaling by a learnable parameter, but there's usually no shifting parameter either. So the RMS is only doing rescaling. It's not doing any recentering at all. To compare with batch norm and layer norm, RMS norm's normalization process is simple and without overhead of calculating mean and variance. Additionally, RMS norm claimed that the scaling factor is more important for stabilizing the norm compared with the shifting factor. So that's why they're not doing any of the shifting recentering. So RMS is actually preferred in many scenarios where computation efficiency matter. You can see for a lot of recent models like the Llama version of GPTs, and then for DeepSeek, they're all using RMS norm, so it's definitely catching up. So this is the formula for RMS norm. You can see it's a lot more simpler. There's no additional steps, just one. AI is the activation for the ith neuron, and you have to first calculate the RMS for A. It's basically adding up all the AI square and then divided by n. N is the total number of features, which is the total number of neurons in the input vector of this specific layer. And then there's a scaling factor. This again is the scaling factor, that parameter that I mentioned. It's learnable and it's applied right here. So this is RMS normalization. It already looked a lot simpler than layer or batch normalization. All right, hope this helps. Thank you everyone. If you like my video, please subscribe, like, or comment.